It's my pleasure to actually kick off this event by asking our Dean of College of Engineering, Shankar Sastry, to open and say a few remarks, and we'll go on from there.
Okay, thank you very much, Iklak. I know I stand between you and some exciting presentations. It's a real pleasure and privilege to have the Center for Entrepreneurship and Technology part of the college, and especially this particular contest in clean technologies is a particularly useful one to us in the college this year. As I was telling Nat and out here in the front row, you know, we've just been involved in trying to help Tom Siebel think through rules for a zero energy home competition, which will be announced, we hope, later this year. You know, it'll be a contest where it's not only zero net energy on new homes. Homes occupy 40%, 39% of energy consumption, more than that percentage of the carbon footprint, and so on and so forth. And the question is really, how do you build zero net energy homes, and to do so with actually zero net cost, which means to say that somehow you can't just put $1 million of photovoltaics on your roof and say it's zero net energy. You sort of got to figure out how to pay for it. And so I think that we will be using the auspices of the Venture Lab and also some of the energy that this competition has generated to encourage some of the Berkeley teams. This will be an international competition. It'll be off, we hope, in about October this year. And even though the focus will be on energy homes, zero net energy homes, I do think it'll be broader. LBL is just kicking off a project also called HyperBrick, which is also for zero net commercial buildings. As you know, the California Energy Commission is moving towards the zero net energy model by 2030 and 25% energy for retrofits and so on and so forth. So there's a regulatory backdrop to all of this. So this is, of course, in addition to all the other kinds of solutions that you're going to be hearing about. And the reason I'm telling you this is, you know, this is a $20,000 contest, but it's a pretty important contest because, you know, the kinds of rules that you have here really have formed a point to inform us of how we can work with Tom Siebel in putting together the results for his competition, which will really be a $20 million competition. So I'm really very pleased. I'm just going to be a spectator and listen to what comes in here, and I won't overstay my welcome. So I'd like to thank especially the judges and the sponsors of this event for dedicating their time to this event. I always joke with Iklak that the caliber of folks that come to this meeting are people who wouldn't come to campus if I invited them, but they're always very happy to come and talk to the students, so I'm grateful. Thank you very much.
Okay, so I think we're going to pretty much get to it very quickly now. There's probably a couple things I should just tell you about what's going to happen now. So all of the teams, there's 16 teams, you're going to go one by one. And you're going to have 3 minutes, and that 3 minutes is relatively strict. In other words, if you're still on slide 1 after 3 minutes, you're going to have to go anyway. So use your time carefully. We're going to have timekeepers so that they'll let you know when 3 minutes are coming up. But use your 3 minutes. There'll be no Q&A in these 3 minutes. The judges will use your presentation, your best pitch, if you will, to figure out which 4 teams should come back for Q&A. Based on those 4 teams, all those 4 teams will win something. So those 4 teams are winners for sure in the competition. Out of those, based on the Q&A, we will award a first and second place. We'll decide who's going to go to Copenhagen and so forth. I think at this point, I think the one thing we should do before I turn it over is that we should have the judges stand up and perhaps just introduce themselves, or I can help with that. Let's start with Shomit, please. Okay. Michelle?
Sarah Peach from Siemens Technologies, the Business Center for Jerry Fiddler, I'm an independent investor, founder of Wind River Company in Alameda, and chairman of Solar Scientists in Biofuels.
Al Flash, I'm director of commercial technologies at PG&E. Matt Goldhaber from Claremont Creek Venture, the finest venture fund, without any doubt.
Okay, here, hold on, we have. Just a second, Colin.
Colin Falk, in trading and risk management office.
What?
I don't want to see it. I'm Mark Albert, corporate partner at Purpose GUI, which basically works with real estate companies.
I'm Jack Kirok from SunPower Corporation in San Jose, Richmond Solar Energy Company.
Michelle.
Hello, I'm Michelle Klein. I'm with Flight Ventures as a venture capital arm of Ventures.
Okay. All right, then I think our, are we all set then? Anthony, are you ready to take over?
Yep, I'm here. So we're gonna start with team number 1, of course.
Okay.
And so if team number 1 is there, who's presenting for team number 1? Are you? Okay. Do you put up the slide?
Test.
Hello.
All right.
How are the acoustics? Can you all hear me? I'll use it.
All right.
Is there a ready, set? So let me just say. Okay. So we're OmniOx Biotechnology. We are a startup company based out of Berkeley. John Winger and I did our PhDs with Michael Marletta. He's the chairman of chemistry at Berkeley. And we're going to talk to you about an exciting technology that is coming out of Michael's lab. And we've got a great set of people, all with Berkeley connections, helping this venture become a viable near-term commercial entity. So in the last 48 hours, the world consumed about 6.6 billion gallons of gasoline, which is about 1 gallon per person. And if the promise of biofuels is to be met, using microorganisms, scale-up is a huge issue. Can we make microorganisms productive at scale to meet the global demand for renewable sources of energy? Even if we dedicated all US corn and soybean production to biofuels today, we'd only meet 12% of US gasoline needs and 6% US diesel production. And that's because if we're turning to microbes, which this picture was taken a couple 100 million years ago, you can probably see the Brontosaurus and the pterodactyl. But microbes have spent a long time figuring out metabolism in very different environments from where we're asking them to do it, and that's in bioreactors. So we're taking microbes out of this environment, we're putting them in here when we're asking them to make fuels or chemicals. And the great challenge is the tools that we need to dramatically boost the potential for scale-up are separate from the kinds of technologies that are being developed to just make the fuels in the first place. And so there's DuPont has recently opened the largest aerobic fermentation plant in the world. It's a $100 million plant in Tennessee. And their goal is to make a specialty chemical called 1,3-propane-diol, which is used in manufacturing for a number of different products. And they're competing against the fact that the cost of production using petroleum sources is $1 a pound. The manufacturing process to make a bio version using E. coli consumes 40% less energy and 20% less greenhouse gas. But the challenge is, can we make enough? Can you really scale up in these aerobic fermenters? And it's clear that if you can, yield enhancements, scale-up enhancements are directly tied to profitability. So the major problem with aerobic fermentation, and it's not just for specialty chemicals, it's for pharmaceuticals, it's for biodiesel, it's for other manufacturing, is how do you take a microbe which normally has plenty of access to oxygen in the world and stick it into a situation much like higher organisms or humans where it's just where there's so many cells you need a better way to deliver oxygen. It's the surface to delivery problem, surface area problem. And at Berkeley, we've developed a system to give lungs to microbes. It's a protein technology where we've been able to tune oxygen binding across the entire biological
I'm going to have to cut you because these 3 minutes are up. I'm sorry about that. Thank you very much.
Thank you.
Can I ask team, are you team number 2? You're team number 2?
Yes, I am team number 2.
Then we can start whenever Manoj is ready. Do you have the clicker?
Yeah, you're very good. All right. Hi, I'm John Waldeisen on the left, and I'm a first-year graduate in bioengineering. And my comrade is Linda, and she's currently in British Columbia, Vancouver. And she hopefully wishes to enroll in the Environmental Health Sciences program this fall in Masters. And together, we are proposing an in-car carbon monoxide detector. So the in-carbon monoxide detector. Now let me sensationalize for a little bit here. Millions of Americans imagine this when they buy a car. Free open roads, clean air. But in actuality, it's a little different if you're driving through Los Angeles during traffic. So although you aren't likely to die from carbon monoxide poisoning when you're driving your car, motor exhaust does account for 80 to 90% of carbon monoxide emissions in urban areas. And carbon monoxide is the #1 cause of accidental death in the United States. It is also noted that exposure levels of taxi drivers and traffic police are deemed scientifically poisonous. In a paper published last year, even small doses of carbon monoxide can affect premature pregnancy, or premature birth and pregnancy. The reason for all this is a cold catalytic converter. And carbon monoxide is not the only result of this. You have oxides from nitrogen, you have soot and particulate pollutants, and you also have unburned hydrocarbons from your gasoline. So with this device, it is a carbon monoxide signal, but it is also an indicator for these other pollutants. So the first objective is to raise awareness in the public. This can be done because this device costs less than $30 right now because of technology coming off patent with semiconductor metal oxide sensors. So by raising awareness, this is our main objective. Our second objective is actual carbon monoxide detection to people at risk, such as people with heart disease, pregnant women, children, taxi drivers, traffic police. And here's my advice. To end this, Linda wanted me to end this with a quote from a Canadian philanthropist, since she's Canadian. So I quote, "We drive into the future using our rear view mirror, using only our rear view mirror." And thank you for your time.
Okay, team number 3, I'm going to adjust the mic maybe. Let's come up here. Is that right for you?
Sure.
That's tough. Readjust it if you need.
I'm not touching. All right, thank you. My name is James Wilcox. I'd like to talk to you about the materials that Mark Adoof and I have been developing at Lawrence Berkeley National Lab as part of the Batteries for Advanced Transportation Technologies, aimed at developing low-cost, high-performance cathode materials for lithium-ion batteries. As we all know, as the cost of oil continues to increase and there's growing concern over global environmental change, there's a strong drive to develop hybrid vehicle technologies. And whether you're talking about plug-in hybrid electric vehicles, traditional hybrid electric vehicles, or even EVs, all these batteries need to deliver the highest amount of energy and power density per unit weight and per unit volume as possible. What we can see is while the current generation is based on nickel monohydride systems, when we can transition to lithium-ion systems, we should see an immediate improvement in both performance and efficiency. However, unless you have $100,000, you can't do this. And the reason is the cathodes are just way too expensive. We're using lithium cobalt oxide materials right now, which are great for consumer applications, but they're far too expensive. So the state of the art has kind of moved to mixed transition metal oxides, where now you're mixing nickel, cobalt, and manganese together to get the performance you're looking for. When we find we add nickel, you get higher energy densities at moderate cost, but it hurts your power and thermal stability. You add cobalt, you get higher power, but you get it at an extreme cost. Manganese, it's very low cost, but at the same time, it's not electrochemically active, so it's actually diluting your energy densities. And one material has kind of come out of this, and that's lithium nickel 1/3, cobalt 1/3, manganese 1/3, which will replace lithium cobalt oxide for consumer applications, but still too expensive for our application. Instead, we focus on lithium nickel 0.4, cobalt 0.2, manganese 0.4 O2, which is better in terms of cost, but the power is still too low now because the chemistry's been changed. And so what our effort has been is, can we incorporate something like aluminum and do it in such a way that we can actually find that we have higher energy and power at significantly reduced cost. And it turns out that we can actually do this very well. It turns out when we add just 5% aluminum, we can get a significant improvement in the rate performance of these materials. We can see a 10-time increase in the capacity that's delivered at a 2 to 3 C rate over a material that does not contain aluminum. And this is important because this is exactly where PHEV would operate. Finally, we've reduced the cobalt content by 85% with respect to lithium cobalt oxide. We have less than half of the cobalt, and it's lithium nickel 1/3, cobalt 1/3, manganese 1/3, and yet we've improved the performance. Kind of in conclusion, this one we developed a very high capacity, very high rate cathode material for hybrid vehicle applications. We've drastically reduced the cobalt content, which should directly lead to lower battery costs. I haven't talked about this today, but we actually anticipate improvements in safety, abuse tolerance, and lifetime through the incorporation of aluminum. And finally, I just want to end by kind of emphasizing that this material is kind of unique in that it could be a drop-in replacement for what's used today. So if it's put in the right hands and optimized in the right way, it could actually be very promising in the near future. I'd like to thank you.
Thank you very much. Team number 4 now.
All right, so we are Allopartis, and we're dedicated to making better enzymes for better biofuels. And what do I mean by better biofuels? I mean looking beyond corn ethanol. We need something sustainable that's really going to bring down greenhouse gas emissions, and also something that can be scaled up to address future increases in demand for energy. Cellulose as a biomass is ideal for this because it's low cost, grown properly, it has a very mild impact on the environment, and it can be grown in the kind of supplies that you need to satisfy the predicted demand for total biofuel use. So how do you make cellulose-based biofuels? First, you start by harvesting the biomass, then you pre-treat it to separate the cellulose from the rest of the plant matter. The next step is the enzymatic digestion, which breaks down the cellulose into its component sugars. That's the one we're targeting. Those sugars then go into a biofuel production process. And one thing that's important to point out is the enzyme process is one of the most expensive ones. And it's not because the enzymes themselves are expensive. Prop time. It actually takes, for 1 gallon of biofuel, it takes 90 grams of enzymes. They're extremely inefficient, and so our solution is to evolve better enzymes. Put those down. Evolve better enzymes to make better biofuels. So the way we do it is with our AlloScreen technology, which is comprised of 3 components. The first is an emulsion, which is tiny droplets of water inside oil. Each of these droplets can act as a miniature test tube in which we could perform a chemical reaction. The reaction that we use is directed evolution. So we take the directed evolution steps, which can take an enzyme, evolve it over multiple iterations and increase its efficiency, put those into the droplet, and then use the third piece of technology where we actually target solid cellulose. This is important because this is what will actually be broken down in a biofuels manufacturing process. So we put the enzymes together with the cellulose in the droplets. We run directed evolution, look to see if the enzyme degrades the cellulose. We pick that, send it in through further rounds to improve it iteratively. Don't pick it, then it goes to the trash. One of the key advantages of this screen is that competing technologies can look at millions of enzymes, screen millions of enzymes per day. We, with this technology, because of the droplets, can do billions of enzymes. And this can quickly get us to better enzymes for better biofuels. When I say better enzymes, I mean, in a short-term goal, 10 times more efficient. And what this does is take it from 90 grams of enzymes that you need for biofuels down to 9 grams. So this decreases the cost of production, speeds the process, and then for the consumer, the big picture is we we lower the total cost of production of enzymes so that we're competitive with...
Time is up.
All right, thank you.
I have to cut here. Thank you very much. Team number 5 is up. You want to lower the mic, maybe? Is that fine with you? Oh, yeah, it's a clicker.
Top one?
The top one is the forward.
Good afternoon, everyone. My name is Sarah Biani, and I'm speaking on behalf of the Advanced Affordable Solar Water Heater team that's made of engineering, public policy, and business graduate students. Our technology is a domestic water heating device that will allow households to lower their energy costs for heating water. Unlike electric inline heaters, gas heaters, and lumber, our product is safer and more sustainable from a financial, manufacturing, and environmental standpoint. And here's why. Currently, in developing countries, domestic hot water is obtained unsustainably with non-renewable resources that are not affordable and are environmentally problematic, and most communities have limited resources, access to these resources. And so our goal was to develop a low-cost solar water heater that would be affordable for low-income households in developing countries at a market price of $100. A solar water heater system consists of a solar energy collector and a water storage tank. Our system is a classical compact design that both heats and stores the water with a novel use of materials such as a plastic water bladder that's insulated, covered with a layer of metal sheet and glass sheet. The third prototype that we built in Guatemala this spring is at an estimated price of $126 that includes both labor and materials. It's effective at heating water to 40 degrees Celsius, which is important for proper hygiene, and it's made out of materials that are locally available and durable. And it's also easily manufacturable and easily installed and maintained. Our initial test results indicate that our system achieves the goals of the 40 degrees Celsius, so it is a viable technology. Our initial target community are the urban households in Xela, Guatemala, most of which use the electric inline heaters for showering. And from our initial market survey of 96 people, 72% said that they would pay for $100 for the system. And they were willing to even pay more than that to be able to decrease their electricity bills. From an economic analysis indicates that there's a potential revenue of $1.5 million just for the city alone. And with that, I thank you for your time.
Thank you very much. Team number 6. You have the clicker? You do?
Hello, my name is Shondeep Ghosh. That's Matt Evans and David Schultz. We're the founders of Banyan Energy. Also graduate students here at Berkeley with backgrounds in mechanical engineering, materials science, physics, and business. So Banyan is focused on the solar power industry and really interested in how to move the industry from where it is today, which is gigawatts of annual production, to where it needs to be, which is terawatts to solve the clean energy problem. But the problem is that today's silicon panels are very expensive and require an incredible amount of capital expenditure in order to make them. So what our solution is to replace the expensive solar cell material in panels with cheap optics. We developed a novel optical platform technology that can concentrate sunlight anywhere between 2 and several hundred. What's unique about these optics is two things. First is that we use total internal reflection in order to get superior optical performance. And second, and this is key, we have an order of magnitude more compact than other concentrated technologies, which means that we can do concentration up to 10x and beyond and still fit into existing panels, use existing production equipment, use existing installation processes and materials, basically leverage the food chain for solar that already exists in the world and get a lot more from it.
So here is what our optical platform actually does. We use data for our 10x concentrator product for this example. By replacing expensive solar cells with inexpensive Banyan optics, we're able to reduce manufacturing costs per panel by 33%. Even more important than that is the impact that we have on scale. The solar panel industry faces end-to-end capital expenditure requirements in the billions of dollars. With our technology, we are able to reduce that capital requirement by up to 80%. So here's what we've accomplished so far. In the last 3 years, we've done extensive optical design and modeling work to verify the optical performance of our design. We have built 2 successful conceptual prototypes, one of them pictured there. We've begun initial panel design and manufacturing process work, and we've begun speaking with potential customers. These customers have indicated strong interest in our ability to solve the biggest problems in solar, which are cost and scale. Thank you.
Thank you. Team number 7. Get the clicker here.
Good afternoon. My name is Sebastian Humbert, and I'm glad to present you the project, which is an interactive online database of company environmental footprint. So the team, I'm a finishing PhD student in environmental engineering, specialized in life cycle assessment. I work for 4 years in LCA consulting, and we also have one person specialized in social corporate responsibility, one person in online publishing, and one person in web-based interactive solution. So the key is that the team has a complementary skill to make the project successful. The problem, there is a lot of environmental information that exists about companies and their product online, but the problem is that they're scattered, unorganized, and often one-sided. There is a rare or no platform that enables consumer to make an active choice by providing an objective quantitative overview of the environmental impact of different products or different services of companies. So we want to help the consumer to become consumer actors. So our solution and contribution is an interactive web platform that is LCA-based. It means it provides quantitative and objective information. Consumer can choose the indicator. It allows for easy comparison between products and services and companies. For example, if you have a restaurant and you want to choose between Pepsi and Cola, you can look at which one has the least environmental impact. These 3 sections, validated information, company provided information, and public edible information wiki style. This is a triangulation that enables a holistic view of the company impact, which is a key difference from most of the other environmental online sources. This will help the world because it's an incentive for companies to reduce their environmental and social impact for PR and develop more responsible products to appear more competitive in the ranking, in the comparison of products. Feasibility, technically not difficult at all. It's a typical online platform. The section that is open is a wiki style, where people can enter information, and you could look at companies that produce products that are comparable. Online calculator are not a problem. Our team has an necessary skill. I've worked for 4 years in life cycle assessment. One of our colleagues already developed an online LCA software. And companies will be interested in this project because they want to know the scientific, the absolute impact, but also the public perception of the impact. And this project is exactly in the middle. It benefits both consumer and companies. That is the reason of the expected success. Startup costs are small, less than $100,000 to have the project running and being online. I thank you for your attention.
And thank you very much. Call team number 8. If you want, Just be careful with that. It should be okay.
Hi, my name is Craig Jacobson, and I work with a team of researchers at Lawrence Berkeley National Lab in solid oxide fuel cells. These are fuel cells that operate at high temperature and can convert conventional hydrocarbon fuels to electricity. These fuel cells are generally made out of ceramics. Our contribution to this field is basically we've gotten rid of the ceramics and brought in a material that's 20 times cheaper and many times stronger. That's stainless steel. And Mike will give you a short demonstration of the difference between the ceramic and the steel.
Yeah, this is the traditional all-ceramic fuel cell. And I'm going to crush it with our new metal-supported fuel cell to show you how much more rugged it is.
All right. You don't want that in your car. We win. All right. What are we going to do with this fuel cell? We're going to go into developing countries and provide lighting. It's about a $38 to $50 billion a year market. Right now it's being served with kerosene. At $100 a barrel oil or more, there's a lot of pain in this marketplace. They're looking to replace this. So what are we going to do? We're going to replace it with a small fuel cell. Now, of course, many people think developing countries, let's go solar. Okay, solar is actually a very expensive technology. The payback on that is measured in years. And in addition, if you're into the monsoon season, you're out of luck, you're out of light, and you're going back to kerosene. Our technology does work with kerosene. It will reduce fuel consumption by 80–90%. You're going to get 20 times more light, and you're going to get a payback in about 1 to 3 months. That's something that people can afford. What does technology look like? These are cells that we actually test in our labs. They're very small steel cells, and if you're from PG&E, you go, well, who cares? But this will actually generate about 1 watt of power, and that's all that you need for these LED lights. The estimated cost for this is about 10 to 20 cents. Again, that's something that people can afford. And again, as we said before, it's very rugged, robust technology that's suitable for the real world. And I'll just end with a few takeaway points. And again, we are actually the leaders in this field. There's many people following us, but we're still a couple years ahead of them. Again, it's a market that has relatively large pain, but the performance thresholds are actually relatively modest, and this is a technology that can step into that gap. And again, we have a lab scale technology that is very close to meeting those market needs. And again, if you'd like to contact us, my email is cpjacobson@lbl.gov, or you can talk to Mike or Grace or Tal, some of the other people on the team. We'd be glad to discuss this with you. Thank you for your time. Thank you for your attention.
Thank you very much.
Hi, everyone. Thank you for having us. My name is Annabelle, and these are my teammates. Kenneth is a third-year mechanical engineering PhD student, and Kunal and I are second-year MBAs with energy backgrounds. We are here today to present a commercially viable solution to harnessing ocean geothermal power. So as we know, with climate change and the rising energy demand, the need for renewable energy on a large scale is becoming increasingly important. One source of renewable energy comes from the ocean. One long-promising technology is OTEC, which generates electricity using the ocean temperature gradient. But OTEC's implementation has so far been limited due to 2 main problems, which are its low thermal efficiency and high capital costs. Our solution addresses these 2 problems, both from a technological and business standpoint. First, to increase thermal efficiency, we can harness the geothermal energy that is available beneath the ocean to maximize the thermal gradient. To reduce capital costs, we have identified an opportunity to retrofit decommissioned oil platforms that are located near these geothermal vents. With geothermal power, we use the high-temperature water of 300 degrees with much cooler surface water in a combined cycle to generate electricity. We calculated this process to have an efficiency of 23%, producing 30 megawatts of electricity per facility. Now, by comparison, OTEC is 6% efficient, and it's only able to produce 1 megawatt. But what makes our solution unique is that we can produce 30 megawatts of clean electricity using an old oil platform. Now, this use is appealing to oil companies because these platforms often represent an environmental liability and financial burden to them. We calculated the cost of retrofitting a platform to be around $85 million, or 53% less than a new construction project. We use GIS mapping tools to identify locations where platforms were optimally located near geothermal vents. And we consider our target markets to be coastal areas with geothermal activity, decommissioned platforms available, and most importantly, buy-in from utilities, oil companies, and government. To give you an example, we calculated the revenue potential in coastal areas like California to be around $8 million per platform per year. So just to give you a quick idea of our action steps, right now we're in the process of applying for a patent, and we have also spoken to a few oil companies who have expressed interest in retrofitting platforms for innovative new uses. Going forward, we will be validating our technology by doing more field research and evaluating various revenue models. So in closing, we're confident that our solution can create a value proposition for all of these parties involved, with the ultimate goal to harness ocean geothermal power in a more economical and sustainable manner. Thank you.
Thank you very much. Team number 10 should come up. Yeah, can you pass the clicker? Thank you. Okay. Yeah, probably.
Can I see it on here? No, it's not going from JTS. Which one's the slider?
This one is forward, this one is backward. It's pretty easy.
Ready? I'm Nathan Oda, a researcher at UC Berkeley. I'm here to talk to you about Aptility, the company I founded to commercialize my PhD research for energy efficiency and demand response in homes using wireless sensor networks. The research was funded by the California Energy Commission. Our team has more than 2 decades of experience in wireless embedded systems and 3 decades experience in the utility industry. Heating and cooling our homes is expensive. It costs about 500 million metric tons of carbon dioxide emissions a year to heat and cool our homes. That's more than all of Mexico uses. The average home emits about what an average passenger car emits in 1 year. It's expensive to our wallets. HVAC is also a peak contributor to the peak electrical demand we face in this country. The culprit is the 75 million houses with central HVAC. How do we reduce the demand? Our wireless control solution reduces carbon emissions through energy efficiency and demand response. Wireless sensors in every room transmit temperature and humidity readings to a wireless controller that uses our patent-pending algorithms to control comfort, and we send that to our wireless thermostat that uses existing wires and simple on-off control. Using simulators from LBNL, we compared our multi-sensor control strategies with a programmable thermostat. This chart shows the potential energy savings on the x-axis versus the potential comfort improvement on the y-axis. Above the red line shows that we can simultaneously reduce energy and improve comfort. Below the red line shows that we can provide a robust design space for trading comfort and cost during demand response. This is one example of a house in Pleasanton with our system in it. The bottom line is that using industry-proven methods to evaluate comfort, we can simultaneously increase comfort in the house, reduce temperature range between rooms, and reduce energy consumption by up to 30%. If this homeowner had our technology, he could save about $125 per year and avoid 1 ton of carbon emissions. If you extrapolate this to the national level, our technology has the potential to avoid 150 million metric tons of carbon dioxide emissions annually. Our system is also capable of automatic demand response. Here, our testbed system in the bottom communicates live with California ISO to modulate the air conditioning duty cycle in response to the load on the California grid shown in the blue line in the top graph. I'm Nathan. This is Aptility. Thank you for your time.
Thank you very much. Team number 11, come up. Did you get the clicker? Okay.
Hi, my name is Anthony Pavasiliou. I'm a second-year PhD student in Industrial Engineering and Operations Research. The other members of the team are Mauricio Junca, a PhD student in Industrial Engineering and Operations Research, and Tomas Tigov from MBA School of Business. The problem that we are addressing in our project, everything's going wrong. Oh, the top, excuse me. The problem that we're addressing in this project is the large-scale integration of wind power. Main problem with wind power is that it varies randomly and in great magnitude, and this causes financial penalties for wind generators. It causes the requirement for investment in system backup, and it sometimes causes rejection of supply even if wind is available. And this makes wind unable to compete for large market shares in the power market. The approach we're taking to solve this problem is a direct link between wind generators and loads which can defer their demand for power. When we, suppose you want to do your laundry, you wake up in the morning, instead of doing your laundry when you're back, you place a request to a wind generator and ask that in the next 8 hours that you're in work, the laundry is done. That gives the wind generator a valuable time window within which time it can anticipate the coming of wind. If there's a lot of wind, then it can satisfy your demand and sell the excess potentially to the spot market. If there's not enough wind, it waits to satisfy your demand and, if necessary, covers the short position in the spot market without disturbing grid operations, and that's the key to our project. Now, in the case of, so given these two degrees of freedom, flexibility and the spot market, it's possible to see wind getting a large share of the power market without disturbing grid operations. And in the case of a large wind plant with many customers, these, deferrable demand has to be scheduled. I have to schedule all my customers and simultaneously decide how I'm going to bid in the spot market. And that's the reason we're developing software which automates this trading process. We have simulated the performance of our software for large-scale integration in California. What's clear is a dramatic cut in costs, which enables us to charge electricity at a lower price in order to entice flexible loads and gain and still increase our profit. What's special about the proposal is that it integrates well with market operations and existing communication and control technology. And the key from the simulations that we need to keep is that wind is extremely, flexibility is extremely valuable for wind. And wind should be able, by incorporating this technology, to gain the flexible market. And that could potentially be 15% of the things we do. Think about how many of the things we do are deferrable. Wind should have the incentive to grab these and pocket them and benefit the environment. Thank you.
Team 12. Team 12 should come. This is the one.
American consumers are bombarded with messages and imagery about the threats of global warming, which has led to significant anxiety and concern. This anxiety has led many consumers to ask themselves a very simple question: what can I do? We will help consumers answer this question. We will give them the information and tools to reduce their consumption of electricity, save money on their utility bills, and reduce their carbon footprint. Our solution is easy to use and inexpensive, and our business model innovation will yield rapid customer adoption. We focus on home electricity because appliances use a lot of power, and energy efficiency and conservation represents one of the easiest and least expensive ways to reduce carbon emissions. The problem is that many people just don't know how much electricity they use and how much energy and money they can save. Furthermore, research indicates that improved information and control results in electricity savings of up to 10%. At this rate of savings, the payback for our consumers will be as little as 1 year. If we achieve 10% adoption, our solution will have an equivalent impact of taking 1.6 million cars off the road. Our system consists of hardware and software. The hardware is a small pass-through device that plugs into electrical outlets around the house. You simply plug the device into the wall and then plug your appliances into the device. The device measures the electricity consumed by the appliances and wirelessly transmits this data for display on any internet-enabled device. It also has the ability to turn appliances on and off. The web-based software has many compelling features. For instance, it will allow me to realize that my old freezer in the basement uses 20 times more power than the national average, and help me calculate the payback period for upgrading. Or from the office, it will allow me to see that I forgot to turn off my air conditioner at home, and allow me to do so from work. We will aggregate consumption data and have a communication channel to each of our customers. This enables us to form mutually beneficial partnerships with retailers such as Best Buy. Retailers get access to direct advertising, we get access to distribution capabilities, and retailers are incentivized to aggressively sell our products in order to increase their advertising base and improve their green profile. For instance, if a user has an inefficient refrigerator, we can contact that person and suggest a replacement from Best Buy. Once we establish a large installed base, we'll leverage our communication channel to offer demand response solutions to utilities. So our revenue will come from three sources: from the sale of hardware to customers, through a one-to-one marketing channel provided to retailers, and in the long run, through the sale of demand response solutions to utilities. Our technology exists today. These are components from our prototype hardware, and our software is currently under development. We leverage existing technology to take advantage of the most easily achievable energy savings. To conclude, our team consists of 4 Haas MBAs and 2 computer science PhD students from the Wireless Embedded Systems group. As you can see, we have diverse backgrounds and experiences that will allow us to make this venture a success. Thanks for your time, and we look forward to taking your questions.
Thank you very much. Team number 13. Press this button.
Sounds good, thank you. Good evening. I'd like to present Elysium Renewables, a next-generation biofuel company. We're seeing the spin-off of technologies developed in Dr. Jay Keesing's laboratory at UC Berkeley. We are addressing 2 problems. The first is currently we rely on petroleum for our liquid-based fuels. The second is that currently we're using ethanol, a bad biofuel. Why is ethanol bad? First of all, there are high energy costs to produce biofuels. Today, ethanol companies are virtually making no money. Natural gas and distribution costs are primarily due to ethanol's inherent ability to absorb water. This means you must distill it and you cannot ship it by pipe, instead must transport it by rail or truck. As we go into more detail, we directly address this problem. So it requires more energy to produce ethanol than you actually get out of ethanol as a liquid fuel in your car. Further, there are high environmental costs to produce ethanol. 15 liters of water are used for every liter of ethanol produced. And this costly distribution infrastructure I mentioned entails that there are high distribution costs for ethanol producers. Aventine Renewable Holdings saw its distribution costs rise 36% between 2005 and 2006. So the problem is getting worse. However, for us, this is kind of great. The market is getting bigger for our solution. Currently, we produce 7.5 billion gallons of ethanol today, with an anticipated rise of almost 13.5 billion gallons of ethanol by 2017. What is our solution? We have core competencies in synthetic biology, metabolic, and protein engineering. Our technology is feasible and credible. We've already produced next-generation pharmaceutical products were spun out of our lab, and the company is worth over $500 million today. Our biofuels work is developing biofuels that do not mix with water. We have targeted biofuels and molecules from nature and are engineering industrially tractable organisms to now produce them in the exact same infrastructure that you can produce ethanol in. So the key point being, when these biofuels do not mix with water, you do not need to distill them, you can ship them by pipe instead of moving them by truck and rail. So what is the value proposition? Our biofuels are better. When we blend them at less than 1%, we have a 4% increase in fuel efficiency. They're 100% compatible with the US car fleet, unlike ethanol today. And we have a net reduction in biorefinery water and greenhouse gas emissions. What this entails for our value proposition to a current biorefiner is a reduction in operating costs of 25%. So the total market value of our product today is $2.25 billion, and with the increase in biorefinery capacity for ethanol increasing by 2015, it'd be a $5.25 billion market. So in conclusion, there are a number of problems with ethanol. We address these problems, probably a strong value proposition, but the end consumer and a current biorefiner who can switch over to now producing our next generation biofuels. We use less water, reduce greenhouse gas emissions, but a net reduction in all these harmful effects while decreasing or increasing. With that, I'll pass on.
Thank you very much. Thank you. Is that a bomb or no? No. Okay. Yeah.
Thank you.
Good afternoon. My name is Andrew Tinka. I'm presenting on behalf of the Lagrangian Sensors System Laboratory here at UC Berkeley. Today I'll be discussing our work in developing and deploying a floating water sensor for use in the Sacramento-San Joaquin Delta, which is a managed river network that supplies drinking water to over 20 million Californians. In 2004, one of the levees in the San Joaquin Delta broke, and over 20 square miles of agricultural land flooded. Silt contamination required shutting down the pumps that extract fresh water. Importing replacement water cost $1 million a day. The question is, how long did the pumps need to stay off? Stationary sensors are poorly equipped to answer that question. The problem with stationary sensors is that the contaminant has to come to you. By contrast, a floating sensor that moves with the pollution through the system yields more data about this medium-term phenomenon. As it turns out, the Department of Water Resources needed to act fairly conservatively and keep the pumps off for 30 days. Later analysis showed that that was too long. But given the information they had at the time, they didn't have much choice. The traditional sensing technology in the Delta consists of a collection of fixed sensor stations. There's about 50 of them in over 1,000 kilometers of channel. The value of the data they collect depends on the relevance of their location in the network. When something unexpected happens, like a levee breach, and the topology changes, the sensor locations may no longer be relevant. Our solution is a floating sensor package. Instead of being anchored to one point, it floats along the water. The most valuable sensor in this situation is the GPS receiver because it tells you where the device is and allows you to reconstruct the flow of the river. Today, our fleet has 10 of these devices. By spring of 2009, we'll expand to 100. They send data home using a cell phone module, and they communicate between themselves using wireless links. There's plenty of room on board the device for secondary sensors, allowing us to sense things like temperature, salinity, and particulate contamination. The other side of our research is the data assimilation techniques needed to take the individual sensor tracks and develop a global view. We use the ensemble Kalman filter because it's a probabilistic view of the system. We get not only a snapshot of the system, but information about the uncertainty of our snapshot. We know what we know and what is still fuzzy. Ultimately, we hope to close the loop and use the uncertainty information to decide where to send the next wave of sensors. This is a capability that is unique to mobile sensing. Our long-term plan is to make mobile sensors part of the sustained infrastructure of the managed Delta. We're working on using small amounts of self-propulsion so that the sensors can stay in the field longer. Ultimately, we hope to develop flexible, affordable, reconfigurable technologies to improve data collection in river and delta systems around the world. Sustainable resource management requires high-quality, relevant data, and mobile sensors can provide that data. Thank you very much.
And thank you to you. So, team number 15. Did you get the clicker?
No, we're not going either way.
Oh, you're not? Okay. You're not going to.
It's not at the beginning. It's not at the beginning. So we're smart lighting, personalized lighting using wireless micro platforms, save energy, save money, and improve quality. My name is Alice Agagino, and my team members are James Bonnell and Yarong Wen.
I'd like to start off by focusing in on annual lighting cost. Globally, this is a $230 billion energy bill with an environmental impact of 2.9 billion metric tons of CO2. More specifically, in the United States, in US commercial buildings, this is an $18 billion energy bill. In commercial buildings, the majority consumption of this electricity is due to lighting at 30%. Our initial proof of concept shows that we have at least a 50% potential savings in this electricity consumption, totaling $9 billion in annual savings in the US. And you ask, how do we do it?
So we did this through individually controllable lighting system using wireless micro platforms. Consider a person walking into the office with a single click, logging onto the system, and applying her preferred light setting. And the lighting in the office will then optimize to deliver each user's preferred lighting conditions while the unoccupied area remains unlit. This requires wireless control modules with minimum retrofitting and personalized setting through multi-mode user interface. Furthermore, we believe that it is possible to save up to 70% of energy when incorporated with daylight harvesting and load shedding building technologies. We've implemented this system to a regular office on campus with 19 overhead luminaires, which were originally controlled by a single switch. And we are very proud to report a 50% savings over the past 1.5 months.
Now, this 50% savings is an impressive number, but we're also interested in user satisfaction, which goes towards higher productivity in the office. We've gotten a lot of positive response, both in terms of the personalization, but also the optimized lighting that the system delivers, and also the raising of energy efficiency awareness in the office and the ease of adoption. I'd like to read a quote from one of the main users. "Before this system, I wasted a lot of energy when I was in the office alone. Now when I come into the office, I can adjust the lights to meet my needs while reducing energy consumption at the same time."
So we showed technological success and user satisfaction. What is the commercial opportunities here? Well, it turns out lighting is a big business. $12 billion alone in the US, $40 billion worldwide. This translates to $9 billion in energy savings in the commercial sector alone in the US. And it's easily extensible to new energy efficient lighting like LEDs, as we show here. Non-energy benefits include increased worker productivity, enhanced mood experience, so it opens up the whole entertainment industry to this sort of technology as well, and improved environmental impact, of course. We've done a complete life cycle analysis to show the benefit is from 200 to 300 times improvement. We've received interest from industry and
cutting you off. Thank you very much. The top one and go forward.
Hi, my name's Iris. I'm a bioengineer here at Berkeley.
Hi, my name is Brian Ye. I'm a second-year IOR student here at Berkeley.
Water waste contributes to the depletion of a very crucial and limited natural resource.
On average, 13% of all water use is attributed to leaks. Now consider in the US, where commercial use adds up to 6.94 billion gallons of water each day. That means that every day we're wasting over 900 million gallons of water.
At a rate of $7 per 1,000 gallons, we are literally leaking away $6.7 million every single day.
To put this into perspective, one leaking toilet per day will leak up to 3,300 gallons of water. A person in a developing country might use only 15 gallons of water each day.
This means that the water wasted by just one leaking toilet could serve a total of 200 people with water in a day. But if we can detect leaks instantly, this 13% need not be lost.
By using piezoelectrics,
or tiny electronic sensors,
and a SCADA system,
a dashboard to monitor these systems,
we can monitor all of our water fixtures and check their water pressures.
By detecting the changes in water pressure, we would know if a leak were sprung and be able to fix it immediately.
Now that we know what the instant leak feedback system is, we have to ask, is it practical? Is there a large enough market?
Is it cost effective?
Will clients be paid back in a reasonable amount of time?
Will companies want to buy the system?
The answer to all these questions is yes.
When we talk about large amounts of water waste, we're talking about the countless hotels,
airports,
theme parks,
and office buildings
that all have huge amounts of water fixtures.
In New York City alone, there are over 5,600 high-rise buildings, each wasting away 13% of their water.
Clearly, there's a large impact to be made in the cities across just America, let alone the world. But what would it cost them?
The ILF is remarkably cheap. In terms of raw materials, there's only one sensor per water fixture, wiring, and one central hub.
One sensor costs $2, wiring costs $1 for every 80 feet, and a hub might cost $100. So if we take a typical 30-story building with about 8 toilets on each floor, the total cost, including installation, comes to about $50,000.
This may seem like a lot of money, but this cost is only half the cost it would take to install the popular automatic water fixtures. In fact, if we take 2 leaking toilets in a building, that might cost up to $1,250 a month. At this rate, the ILF pays back for itself in under 5 years.
But what other incentives would companies have to install the ILF besides saving incredible amounts of water?
By using the ILF, preventative maintenance becomes a thing of the past. Now these toilets and faucets will tell you themselves when they're leaking.
And water bills would be significantly decreased.
But the most marketable aspect of the ILF is that this technology is not going to be ready in a few years.
It's not going to be ready next year or even next month.
It's ready today. We're really excited to bring you the next step in clean technology.
Using using information technology we have right now in areas we never thought possible.
Thank you very much.
Thank you. That was our last team. That was our last team, so yeah.
All right. So first of all, I just want to end this breaking point with a couple points. First of all, I want to thank all the teams for participating. There's a reason why we hold these contests, and we've already satisfied part of that reason today, which is that we want that all of the teams that work in this space, first of all, to know each other. And many times, what you'll find is that we're gonna take the judges back and we're gonna deliberate and come back with recommendations for 4 people to come back and do Q&A. But no doubt what will happen is that different judges will not necessarily agree. And the truth is that depending on the background of the judge or the background of the industry or just various preferences of different people, they'll find that there's actually matches between different teams and different mentors or venture capitalists and so forth. So, which brings me to the second point of why we do these types of competitions, which is that this is an opportunity for any of the teams to follow up with any of the people who are in our mentoring network or our venture capital network or just in general, anyone who's a friend of Berkeley. So whether or not you end up doing Q&A in the next session, that doesn't mean that we don't encourage you to follow up with either people that are here or other people that we could potentially introduce you to. Finally, one reason is we want students across campus that wouldn't normally run into each other, versus MBA students, engineering students, science students, to also run into each other. So with those 3, at least, goals being satisfied, we're going to take a break. And in the meantime, we have catering in the back of the room. You can enjoy yourself, take your time. It's going to take at least half an hour, but probably less than 45 minutes. Half an hour to 45 minutes, then we'll reconvene and do Q&A. All right? Don't worry, the judges are concerned that they may not be able to fight off everybody else, but we've taken care of that. Judges can just go back into the room. All right. All right, welcome back. This is the one quick comment that I wanted to make was in terms of good reasons to hold a competition like this. One of them is also, and I don't know if this came through when I was suggesting this before, but in some cases, there might be reasons to combine teams, and for all kinds of various reasons. Different skills that you don't necessarily have, or different teams that are working on related things, and they might have some synergy. So just think about that. I'm not going to particularly suggest ones, but I think there's really opportunity for synergies there. Now, I think we can just, at this point, go ahead and announce who are the 4 finalists. And again, we appreciate everybody's entry, and again, there's never consensus on these. There's never consensus, never perfect consensus, and of course, do feel free to leverage all of our network and all of the existing judges and mentors and so forth for future, whether you're in the set of 4 or not. Having said that, the 4 teams include number 6, Banyan Energy, number 3, Better Battery Capacity, number 14, the Lagrangian Sensors, and number 8, Low-Cost Fuel Cell. All right? So So with that, we're going to go into our 10-minute Q&A section, and we'll announce winner. All right? Yeah. Here is number 3, number 6, and 14.
Okay, so we're gonna start with number 3 then, or 14. Okay, yeah, that's fine. So team 14 can come up on stage. I'm going to pass the mic along if you have questions. So you can just take this mic.
All right, this is the time when the judges ask questions. So we need, and it's perfectly okay to pull the slides back. Yes, go ahead.
Just to get you guys started, I wanted to ask a question about the use case that you had about the levees. And can you explain how much faster or how much cheaper you could have solved this levee problem or identified the problem using your sensor versus the conventional fixed sensors?
So when that event happened, it took 3 days for the Department of Water Resources to figure out how close the contaminant would get to the pumps. And we believe with the technology we're developing that we could have prevented the 3 days from having pump stop. So in other words, by monitoring the propagation, we would not have needed to stop the pumps at all. So the answer in that case would have been 3 million. Because the pumps were stopped for 3 days.
Oh, thanks. Have you explored any other applications for, it seems like a general technology that could be applied in a lot of different places?
Yes, in fact, on February 8th, we deployed the same technology on I-880 on the highways. So we did a first deployment with 100 of these N95 phones, which I'm going to try to show in a minute. Here we go. And so this is a joint project with Nokia, and the goal was to demonstrate that from cellular phones only, you can reconstruct highway traffic flow and velocity and travel times on the highways. In fact, we're moving into the next phase of this project where we're going to deploy 10,000 of them in November, and this is going to be demonstrated at the ITS World Congress, the Intelligent Transportation Systems World Congress in New York in November of this year. So obviously you can see this is moving at a very fast pace and also very large scales.
If you had the funds to work on the development plans of your dreams over the next 12 months, what would you do to, what would be your top choices for the product in terms of increasing robustness, performance, decreasing costs? How would you put some additional mechanical engineering or electrical engineering to work?
So in terms of the water package, miniaturization, I mean, it's this size so that we can put whatever we want on board and just experiment and have fun with it. If we were in that all our dreams come true stage, we would make it a lot smaller, like down to the size of about a softball, I'm thinking. We would manufacture it in a larger amount, and mechanically, we would add some propulsion on it. We're experimenting with that already, just small amounts of propellers. The idea isn't to make a device that can like swim up and down the delta anywhere it wants, but what we want is to make small changes in the trajectory. So for example, if a device is approaching a junction, it can choose which side it will go down. And we think that with that, we can make an intelligent system that in the aggregate, they can all work together to robustly provide a complete picture about what's going on in the delta. So one device might go down the wrong channel, but together they can statistically provide complete coverage.
Have you considered the logistic on like sending these sensors out, and what would that do to the boating situation or the environment? Could you recover them? What kind of damages and all that stuff?
So the context is right now, we go out on single-day operations with a motorboat, and we toss them in the water and we chase them down ourselves. With the addition of the small amount of self-propulsion, we believe at the very first thing they can do is automatically retrieve themselves. So in the specifics of the San Joaquin Delta, it's unique in that it's an inverted delta. It all goes through one point to get out to the bay. So with only one catching station and instructions to each of the drifters to like drive themselves into the to get into this net near the end of the delta, we're fairly confident that we can recover almost all of them at the end of the mission. Automatic deployment is also not too bad, because with a small amount of propellers, you can just sort of toss them in at the shore and they can position themselves exactly where they need to be in the river. The challenge is, yes, to take it from this like motorboat experiment up to this system which infrastructurally just exists and like doesn't require a human for every single operation. We think the key is that small amount of propulsion and the fact that everything networks in using the cell phone network, which is already there and has complete coverage over California. So the communication capabilities are basically a solved problem.
Can you talk to us a little bit about your defendability and any IP that may be generated from this, and where your special secret sauce is? So is this in your system integration and miniaturization, or is it in your data management and data acquisition?
The idea of the drifting sensor that follows the water channels has been used in oceanography for about the last 5 years. The Argus network of much larger drifters that go out for years at a time is already there. We face challenges in river and estuarial networks, which are much different than the oceanographic perspective, because the topology is so much more confining. Like there's so fewer places you can go that are safe compared to the ocean, which basically is so big you can just go wherever you want. Our secret sauce is in developing some control algorithms that permit path planning and motion control in distributed environments where the currents are essentially arbitrary. There's a lot of focus in robotics in trying to do motion planning in idealized environments. We work on nasty environments where the flow fields are just whatever, where they could be anything. That's something that gives us an edge in river environments.
And I might add to this that in the specific context of the highway where we're deploying that same technology, in fact, we're already filing a lot of patents for the specific reconstruction of the flow fields, travel times, and speeds. Why don't you show?
Specifically for this kind of application, how big of a deal is collecting data for this for water resource management? And can you kind of contextualize that globally? Or is this just gathering some data that nobody knows what to do?
So there's a lot of reasons why this data would be collected. In the specific context of the delta, salmon migration is a really big problem. So if you understand the way the currents are going, you can understand the way salmon are swimming and the way they're going to go to lay their eggs. More specifically, we're also working with a project that will be deployed in Vietnam. There, shrimp farming is a big issue, and understanding the penetration of the salt in the area in which shrimps are farmed. So in fact, there's really hundreds of different problems. Some of them have to do with farming, some of them have to do with contaminant spill, some of them to do with purely environmental engineering issues. So it's really a mine of problem for us that we're dealing with, and therefore the data is of interest not only to the authorities like the Department of Water Resources, but also the farming community and a lot of other agencies or private entities.
So who's coming next? was team number 8. Was that team number 8? I hope I'm not wrong. Yeah, team number 8. We're going to ask you to stand maybe close to the podium, close to the mic here. It's going to be easier to pass the mic to the judges.
You get it?
I've got it, so I'll ask one. I have a couple questions. Is the device refillable? Is it a use once? What's the life cycle?
It's used once. The lifetime of this device is probably several hundred hours, so it's not really refillable, but it's replaceable. Again, the fuel itself, in this case, is kerosene. It can be any hydrocarbon fuel is what generates the energy.
So I could really think of it as a really good AAA battery in a sense. Obviously more power and longer life, but the same kind of life cycle.
Same kind of life cycle, sure.
And how scalable is it? How small and how large can you grow with this technology?
We're looking at very large scale for utility applications. It really depends on the market that you're addressing. For small scale power, obviously this is all that you need. For megawatts of power, you need really square meters of area, and the stainless steel supports can scale that large.
Is this approximately ready for commercialization?
I think for this market, it's approximately ready. Realistically, for other markets where you're talking about a 5-year or 10-year lifetime, like for utility or for combined heat and power for your home, no, it's not ready. And again, that's why we're really presenting this particular picture of this technology.
The expected cost at scale of a single instance of a LED lighting system for home use would be?
We're targeting $10.
And that would last for how long?
The LED lighting itself?
No, the LED lighting lasts forever, but your fuel cell?
This fuel cell would last 6 months to a year. And you would replace it. Again, we're targeting $10 for the actual unit. That piece, again, this is only basically 20 cents. So we'd sell this for another $1 or $2 as a back-end market for this product.
In the context of a clean tech competition, the idea of a use once and then discard item is a little anomalous. I mean, is there anything?
There's no reason you couldn't recycle this. This is stainless steel. Again, stainless steel is the largest by volume material that's recycled in the world.
Can you say something about how you would market and sell this? How you reach your customers?
How I'd reach my customers? That's not really clear right now. Again, there is an established market. There's an established value chain for the kerosene lights that go into the systems now. I think our view is we would look to piggyback on the governments themselves. Again, it's actually the governments that are subsidizing the oil prices, and they're the ones that are in the real pain. So we'd go to the Indian government and say, can you help us? And I'm sure they'd kind of push us in the right direction.
Is it fair to think of this then as a battery for a LED light?
It's not a battery. This is a battery that you continuously supply the fuel for.
But it's a replaceable fuel cell which acts much like a battery. So
in this case, the actual unit itself would be replaced, but you'd also have to replace your fuel supply.
And so how would this compare to a battery-operated LED light?
Batteries are very, very expensive technologies. I don't know how many, maybe Mark, the next team, or team number 3, can really enlighten you about the cost of batteries. But those AA batteries that you put for your kids' toys are extremely expensive technologies. That's one of the technologies they use in the developing countries, and it's one of the reasons they actually pay more for electricity than we do.
So that replace, oh, sorry, Jack, you done?
I am, yeah.
Okay. So that replacement part, that's really equivalent of just like in a full-scale fuel cell replacing a stack.
That's correct.
Okay.
For this application, the stack is essentially one cell.
And the kerosene, how are you reforming the kerosene? What does that have to go through to?
This is a POX, just partial oxidation reaction, so you just partially burn the fuel.
This does not involve any precious metal catalysts. The catalysts that we have for this technology are very conventional oxides. So the reforming would actually be done in the cell, on the cell.
Does this operate at a very high temperature?
About 700 degrees Celsius. That's the temperature that you actually need for reforming hydrocarbons. It's the temperature of your toaster element. If you look, it's kind of glowing red. That's about 700 degrees C. It's also about the same temperature of your exhaust that comes out of your automobile that goes over your catalysts for their.
So the cell is small, but it has a continuing fuel supply which is integral with it. Is that the idea? Kind of a bottle that sits on top of it with kerosene in it?
That's correct.
And you basically toss the whole thing when it's done?
No, you can either refill the bottle if you wish.
Oh, you can?
Yeah, I mean, it's what that exactly is, I don't know, but in developing countries, I doubt they would throw the bottle away. They would tend to be a little more conservative and reuse it.
You'd end up with a village job of somebody coming out and replacing the stacks and refilling the bottles.
That's correct. That's correct. And again, one of the technologies that you look at, again, you have a few watts of fuel cell. Again, you could say, well, you can charge cell phones, right? The cell phones is a big breakthrough technology for developing countries, but if you can't charge those cell phones, they're useless. And again, this kind of technology can scale. We actually envision a whole suite of products coming in after this, not just this single product.
So I take it that you have nice jobs at LBL and they're not leaving. Is there a team that's trying to commercialize this, or do I have that wrong?
The team at LBL is actually larger. The people that you're looking at here are the people that are interested in a venture.
Okay.
This is not just about technology. This is also about this team that would like to kind of take a step aside.
And you've had funding from a host of big national, international corporations interested in energy.
That's correct.
Are they picking this up, or?
We have licenses in most countries around the world. Or some licensee has taken this. They're interested in their own markets. They have their own market channels. They have their own customers. If you're a utility company, they are licensing this for utility scale power. Well, this is not utility scale power. They're not interested in this particular market. Again, that's one reason we have selected this market is there's an opportunity for a startup. There's an opportunity for us to take it. Meanwhile, the big boys can take it in their market of interest.
So with those temperature requirements, it's heating itself, right? It's creating its own, or it's using kerosene, it's generating energy, it's heating itself, and then we're using the excess. Is it always on? Does it, when you turn it on,
no,
does it
you
take
can
a
turn
long
it
time
on,
to
turn
heat
it
up?
off. One of the things, the amazing things about this technology is, again, you can start it up in seconds. Again, the thermal shock issues are really not issues for us here with this technology. So you can turn it on, turn it off, turn it on, turn it off, and we've done that hundreds of times.
You turn it on and off by essentially with a valve, just shutting off the flow of kerosene?
It depends on the scale of the part, but in this it would be just a valve for the kerosene. Again, we envision this particular product to be as simple as can be. I mean, you can't have blowers, you can't have anything. Just a fuel cell generating a little bit of electricity that goes into your LED light.
Seems like this would have been a great demonstration to show the light. Is there any reason you didn't bring one today? Does this product exist? Or is
I'm not sure that we could actually light kerosene in a closed room legally, but we plan on that as a demonstration in the future.
Great, thanks.
What are your failure modes? Why are these wearing out in 6 to 12 months?
This is just the lifetime of the catalysts that we have in there now. The other issue is just the oxidation of these steels. They form a kind of a scale on the outside, and that grows at a certain rate, and these temperatures, eventually that growth will kind of cause the thing to fall apart or become a little resistive. So it's just the growth of these scales and degradation of the catalysts that are actually in there.
But over time, you'd expect that stack life to get longer?
Yes.
As you develop these?
Right. And so we envision this as the first generation of product. Well, again, you iterate, iterate, iterate to get better and better, you get more money in, you make the life longer, longer, longer. Pretty soon we're at PG&E, knocking on your door, say, hey, we have a 10 megawatt unit, do you want to buy it? I mean, that would be the hope.
Would this device be harmed by the additives in gasoline?
I know of nothing in gasoline or any hydrocarbon that would harm this. Most of them, the most aggressive is probably sulfur, and that is not a problem. We've run extremely high sulfur levels, up to 800 ppm of sulfur, which is levels that you just won't see. These are not problems.
And fuel viscosity is probably not a big problem either.
No.
Since you've got plenty of heat.
There's plenty of heat, so that's not an issue, no.
So if you won $10,000, what would you do with it?
$10,000? I think we would probably form the venture, build the first prototype, and then go after the next, probably $250,000.
Elaborate a little more on your licensing and what areas that you are not allowed to touch.
That is an extremely complicated problem. We keep the licensing department at LBL very, very busy. I have to know the licensing very well, but it is a complicated problem because there are so many people involved, so many fields of use, so many scales. I mean, it's a very complicated issue, but we're quite aware of the licenses and what's available and what's not.
We're going to end up on that.
Okay.
Thank you very much. So next is team number 6. There. Yeah, it's better. So they have, because we have only 2 mics.
Okay. Sure.
Yeah, please.
Go ahead, please.
Have you checked, what's the temperature rise you get when you put concentration on the cell?
We haven't really gotten into thermal issues yet in a significant way. We've done some very preliminary work that suggests with an aluminum backplane, we can get within, if you have a 45-degree ambient temperature, you can have a temperature rise of a few degrees centigrade, which ends up being maybe 1 or 2 percentage point reduction in your cell efficiency. But thermal is going to be an issue, particularly once we get past 3x concentration, definitely.
Thank you.
Can you describe the IP you have around the concentrator itself? Is it in the design? Is it in the processing, the method of manufacture?
Sure. The IP is in the optical design. It is how we actually control light through the concentrator itself. We've done a lot of searches with prior art in the concentrator space, as well as with academic and corporate work over the last several decades in the concentrator space. And it's a very different way to manage sunlight, but it is in the optical design. We anticipate, so the stage we're at, we've done a lot of design work. We're pretty early stage. Over the next several months is when we really want to get into manufacturability for the optics. And we anticipate having further IP develop on the process itself.
Given the amount of work that's going on in both low and high concentration in the industry today, what is it that's different about yours that's going to allow you to succeed where so many others have failed?
Sure. So one aspect is the high performance that I mentioned. What total internal reflection. So I should mention that typically what you see with concentrator optics is either refractive lenses, essentially Fresnel lenses, or hard reflection. So you'll have a metal coating of some kind that actually is like a parabolic trough that'll actually reflect light. And what both of those technologies face is a fundamental trade-off between the 2 critical optical performance characteristics, which is what is your transmission efficiency of your optics, how much sunlight are you losing, how much energy are you losing, versus what's the acceptance angle of the optics, which is any concentrated technology that goes above 2 or 3x has to follow the sun to some extent. And the higher levels of concentration, the tighter the
angle at which you have to track the sun. Refractive optics, because they refract light, you end up with chromatic aberrations which shrink your acceptance angle, even though the efficiencies can be pretty good. Reflective optics give you pretty good acceptance angle, but you end up with losses of the hard reflection points. Total internal reflection helps you with high transmission efficiency and high acceptance angle at the same time. So that's one advantage that we see a differentiation. The other is interesting, which is the compactness aspect. So if you look at, again, today's concentrator optics, the aspect ratio is about 1. So if you've got a square foot Fresnel lens, it's about a foot tall to where you get to the cell. And we're an order of magnitude less than that. Our aspect ratio is 0.1, significantly more compact than anything else out there. Is that for us? Okay. So why does that matter? We think that matters because it allows our optics uniquely to fit into existing panel form factors. And between the cover glass and the cell, you can slide a sheet of our optics in there, as opposed to having to build a whole new module with a whole new production process and installation process and so on.
You done any work on the actual tracking mechanism? And if so, can you discuss that?
We actually want to be able to use trackers that are already being built and deployed in the field. There are trackers like SunPower's Power Tracker, which is being used in Nellis Air Force Base. There's other single-axis and double-axis trackers around the world. So we weren't able to mention this in the presentation, but the specific segment of the solar power market that we're focused on is large field tracked installations, not residential rooftops, not commercial rooftops. And what might be interesting information to some people in the audience is that this is actually a significant, it's a large and growing part of the solar market. It's actually growing 3 times faster than the overall market itself. And the reason is that what people find is that if anytime you have an open field or a ground space that you want to put solar, and you want to use silicon panels, it makes sense to bring a tracker on there. Because you actually gain 25% more sunlight over the course of the day from tracking the sun. Now, what we've done some investigation, and it seems like with the trackers that are currently out there, and the issues around when you place panels on a tracker, you get some flexing of the support structures and ground shifting and other changes through the course of the lifetime of the system. You probably want to have an acceptance angle for your optics of about ±2 degrees. And we're designing for an acceptance angle for our low concentration products of ±3 degrees to give us buffer on that.
Do you think you'll be able to use the same tracking technology for the 500X?
500X will require 2-axis tracking. You see a lot of 2-axis trackers coming up in Europe, and there's so this is an interesting evolving industry. You're now seeing companies that are just focused on developing trackers and tracking systems getting more and more sophisticated. So we're starting to see companies that say, here's a 2-axis tracker, put silicon panels on it for now in large fields in Europe or in the US or elsewhere in the world, but we've designed it specifically for high concentration systems as well. So we haven't gone into the details of that, but we're anticipating that part of the market actually, by the time we get to a high concentration product, hopefully the tracking systems will be in place.
Could you just speak a little bit about where you are in the technology development of this, what you've done, what's still left to do, what's your next big hurdle to get over?
Sure. Like I said, we are early. We've done a lot. So what we've focused on is the optical design work. The next step, so the 2008, our focus is get a full working prototype, high performance of the optics, and establish manufacturability of the optics. And then subsequent to that is build a full working module, get it out in the field, gathering data, and then go through to certification, qualifications, and working with customers on adoption. That said, the approach we've taken is, we've done a lot of the IP work on the design of the optics. We've done a first pass cut through most of the other issues that we're going to have to deal with in detail down the road. So we've looked at, how will these optics fit into an existing panel? What would that look like? what would the implication be for the manufacturing production process? Do we need unique customized production equipment? The answer is no. We've started talking to some potential customers as well, both panel manufacturers and equipment providers, and get feedback from them as to whether this idea is interesting and is this something that the industry would want to adopt. And so far what we're getting is cost and scale are some of the biggest issues in the industry, and this approach that is in fact interesting. Sort of like, build it guys and come back and talk to us, they'll be very interested.
Your IP search, you've probably come across some new, maybe even established players that are doing similar work. Which of the potential competitors give you the most pause?
That's a good question. I hate to do the cop-out answer. I'm almost headed that way, but I'll try. The cop-out answer is going to be, we're that different that I don't see any good parallel to us. The closest thing that we have is a company called Solaria, which has a somewhat similar story to what we have. They've got low concentration. It's very compact. It's this tile that fits right into existing panels. Their concentration ratio is a factor of 2, and their next product is to get it up to a factor of 3. And given the technology, the optics that the optical design that they're using dates back from the 1970s. They're not going to be able to use that technology to get beyond 3x. That's the closest parallel that we found to what we're trying to do.
Thank you. We're good with the questions. I think we're going to end it there. Thank you very much. And last team is number 3. Nobody's correcting me. No, who they
are. First, my first question? Okay. Have you compared the efficiencies of your design to standard cobalt or magnesium? I'm sorry, yeah, magnesium or iron phosphate or any of the other type of lithium batteries?
In terms of a lifetime capability and how much capacity we're losing over time, we think when we optimize the system, we should lose very little with the cycle life. You find there's an initial cycle where you do lose some capacity, but then it's very stable from there on out, especially if you can control the conditions in which you cycle it, which is quite easy to do.
Are there any limitations on form factor or scalability or anything?
Well, what we've developed is the active material. What we can do is, once we have the active material, you can design a cell for the application you want. So in terms of form factors, I think that's really up to the cell designer and what the application needs. I think there's a lot of room for it. People don't do it right now because there's just not, it's not profitable to do it. A lot of people just make the 18650 large cell, and there's no custom lithium-ion cells like that for automotive applications. But it could be done. I'm not sure if that's what you're going for.
Yeah.
So the cathode is just one part of the battery. Do you have any plans to, are you just going to sell the cathode, or are you going to develop a whole new battery around your new cathode?
I'll take this question. It's quite a big project to develop a battery. So we are concentrating just on the material, and to that end, we do some work with materials companies, some of whom are in the Bay Area. And I think to develop this further, we would want to team with a battery company. And we are going to be talking to someone from Sanyo next month. So it's very early stages, but definitely we would need the help of a battery company because it becomes quite complex otherwise.
How does it compare to the normal, in terms of thermal issues, to the standard sort of composition?
Compared to lithium cobalt oxide, we'd expect it to be much more stable. It turns out because aluminum itself is not electrochemically active, it actually limits the amount of lithium we can take out of our cell. And that kind of works as an internal overcharge protector. So we can actually abuse the cell more readily without actually inducing a lot of damage in the cell, which will make the cell a lot more safe, a lot more abuse tolerant, and that's inherently built in. So the temperature for when you're talking about when it's going to react and run away and go into thermal runaway, we'd expect it probably to be increased. It can take more temperature, more abuse before that temperature runaway kicks in. And so I think the 3 by 1/3 can go as high as about 300 degrees cell. We expect to be a little bit higher above that.
I understand it's pretty early days, but if you could guess, what do you think the cost impact of this is? Do you think you cut the price of a battery by half, by more, by less?
Well, depending on the cell, the cost of the cathode can be about 60% of your cell. Okay, and if cobalt's over $50 a pound right now, and aluminum is under $1 a pound. So if we, first of all, if we cut the cobalt by 85%, that's a large amount of that. So I guess you could be 20%, 25% quite easily, actually.
Is that enough to actually make them practical for use in a hybrid vehicle? It doesn't. I thought that you would need significantly more price cut than that to actually put them in. Now you get other gains as well. They're lighter and there's other good things about them, but.
Yeah, well, that's it. You're gaining a significant amount of other performance parameters in terms of density, in terms of everything else like that. As far as exactly what the cost to come down would be, it's kind of a trade-off. I mean, who knows, because it depends on what level the car goes in and how the car is designed as well. I think that it may not enable it at this point, but if we get it in there are people out there who'd be interested in this technology, like a Tesla motor type something would be interested in getting a battery like this into their car, right? Because that's the next step for them. And then we could build off of something like that. You need to prove it in these applications first and then work forward.
If you wanted to continue your product development work solo over the next 12 months and you didn't have the facilities that you have access to today, what do you think you'd need in CapEx to move forward?
A lot.
We figured it was a big number.
I would imagine it's quite large. But I think that there's a lot of, I mean, as far as, I can't even pull a number off the top of my head. It would be quite large, probably $100,000, if not more, I would guess, as a start. But a lot of people who are in the materials development, like what we do, you can contract with somebody who already makes batteries. And so you can protect all your IP and what you're developing there. They can make your cathodes and put a full cell together for you at these initial stages. And then after you get those and you start refining that, you can go from there. And once you get those initial results without having to build a whole internal research facility on its own.
Okay, so you don't want to build a factory?
Only if it looks really good.
You quantified cycle life, power density, energy density?
Not explicitly yet. What we've shown here are what are called lithium metal half cells, which essentially we use an anode of lithium metal, which you never use in a car. It works really well for research grade applications, what we do at the lab, where we search for new materials. When you go to start doing the power testing and everything, the anode has a lot to do with it too. So we really need to make full cells of this and to go from there. And there are specific hybrid vehicle cycling and stuff like that we need to do. But we do expect to see quite an improvement, because aluminum alone increases the potential, and that will increase our power and our energy right there.
How much cash would it take to do those analyses?
How much gas would it take?
Cash.
How much cash would it take?
Capital.
Wait a second. We do that pretty well in-house. I'd say you're better with the numbers than I am.
Yeah. I don't know that I can give full numbers, but we do have people that we work with at LBL, others who work on batteries and work on different aspects of batteries, and we team with them to do some of these tests that are essential to characterizing and finding out if this is good material for vehicular applications. And then beyond that, we would be teaming with other materials developers, battery companies, and so forth for the rest of the work, because it is quite comprehensive and can be quite expensive beyond the scope of what we can do. So.
How long do you think it'll take to do those characterizations?
I think probably 2 years or so.
What's the most likely failure mechanism for your cathode, or well, when it's by itself or in a battery? I mean, as an individual component or as in a battery?
In terms of, I guess I'm just not, in terms of an actual failure mechanism, in terms of safety, or is in terms of a business?
In terms of safety. So what physically happens? Okay. What goes wrong with the battery?
Lots of things can go wrong with the lithium-ion battery, which is why you're not seeing them now. Probably the biggest thing I would be worried about would be an overcharge system, and that's something we really don't have to worry about. We've actually engineered in, like I said, an in-house kind of overcharge protection. And so that would be very nice, and that should help us out a lot.
But you haven't developed that yet?
Excuse me?
You haven't developed this overcharge protection?
We've made cells. Just by incorporating aluminum the right way, just through the chemistry of aluminum, it'll actually become an overcharge protector in and of itself.
But that's the most likely failure mode still?
That would be my guess for the thermal runaway mechanism, would be something like that. Anything else would be a manufacturing issue with the cell, which would be outside of the cathode.
So have you thought, this isn't a business plan competition, so I don't want to go too far into it, but have you thought through what a commercialization of this would look like? Would you imagine licensing the material, manufacturing cathodes? What would you see doing with this?
Well, we are talking with the Tech Transfer Division up at Lawrence Berkeley National Lab to work through the patenting process and to think about this. There are a couple other materials that have been out there that people have developed. They start out with a cathode material, and they've actually formed the basis for a company. And so that would be one way to go. If you have a product that you really think the testing looks really good on, you have a niche market that you can really go to town on, you can really move forward quite quickly. That's the thing, we're still not at that point where we'd say, I'm ready to jump in this, let's build our own company around this, let's go. We still have a few more tests we need to do in the short term in order to say, okay, let's run with this. Let's go see if we can get a lot of funding to do this fast.
There's a lot of people out there tweaking nickel, cobalt, manganese cathodes. Is anybody else using aluminum?
We suspect other people are looking at it, but we don't have a way of knowing. They may be looking at it, but they're not talking about it.
Follow up on, okay, never mind.
Thank you very much.
All right, we'll be right back with the winners. All right, so we're going to go ahead and announce the winners right now. The 4 teams can come up. Now, we did one thing. We thought that this is somehow clever or green or something like that, which is that we did not print those large fake checks. We thought that since this was a clean, clean technology innovation, area, there's no use in printing fake checks and styrofoam and so forth. So I'm just going to announce who are the winners, or at least in what order, and that will be it. And we will contact you on how to get you the funds and the money and the trip and all of these things, right? Okay. So, in fact, I think we might even do electronic deposit. All right. All right. So, this is the part where you always have to be careful not to give the wrong one. Here. Okay, no, I'm pretty sure I'm right on this. Okay, so the 3rd and 4th place teams will get $2,500 each. Okay, and you're effectively finalists, which hint, that's a good way to write it on your resume. Okay, so that will be both Team 3, Better Battery Capacity, and Team 6, Banyan Energy Incorporated. Okay, so the second place team is the Lagrangian sensor team. All right. You guys will get $5,000, and you will also receive the travel award to be able to go to Copenhagen. All right? Okay. Now, just so everybody understands, and at least the way I understand it, this conference, CopenMind, in Copenhagen, is the lead kickoff, whatever, conference before they start the discussion for the Kyoto Protocol. So this is a place where you can go and talk about what you're doing. There's a booth and so forth, and people who come by, and so this is a way for you to disseminate the idea that you have, all right? And in particular, it's funded by Kauffman Foundation. All right, and so that leaves us to our winner. Yes, number 8, the low-cost fuel cell. And you will receive $10,000, okay? All right, okay.